Hi, I'm Mr. Miller, and this is a lesson on logarithmic and exponential equations. So here's our first example. We're looking at solving for x to 2 decimal places. And so one way that we can solve this exponential equation is to write it in logarithmic form. So if we change the form, here's what it looks like. Log base 3 of 11 equals x. So this is solved. X equals, and this is the numerical answer. Now, if you know how to calculate that using a calculator directly, okay, so let's say that you have the Desmos graphic calculator and you're going to functions and you go to miscellaneous and you do log base A, and we want to do base 3 of 11. Then here's the value you get. It's approximately 2.18. Let me make that a little bit bigger so it's easier to read. Okay, so that's one way. Now, if you have a scientific calculator and you don't have something like this, a log base A, you just have a log and it doesn't indicate a base. What it means is that you're doing log base 10. And of course, that's not the base that we want here. So it's a little bit of a problem. So in that case, what we do is we take a different approach. So let's say that we take log base 10 of both sides of the equation. Here's what that would look like. Okay, now again, I'm saying log base 10. Log base 10 is the common logarithm, and when we don't write it, it's understood to be base 10. So I'm just leaving that off here. So now I'm going to use a law of logarithms to simplify the left side of the equation. So I'm going to bring that exponent of x as a factor out in front of the log, x times log 3. And so now I just have x times a number equals a different number. And if I want to solve for x, I would have to divide both sides of the equation by that log 3. And it's log base 10 of 3. So here's the solution I have. X equals log of 11 divided by log of 3. And that's a common logarithm, so it's log base 10 of 11 divided by log base 10 of 3. And this is a different form of the solution of this equation. These are the same. So what I'll just show you now, and I'll just prove that to you, log of 11 divided by log of 3 is the same value. So if I do log of 11 and I divide by log of 3, and notice that I have not specified the base here, which means it's using base 10, and I get exactly the same value. So these two expressions are equivalent. So if you have a calculator that does not allow you to specify a different base like 3, and you need to evaluate log base 3 of something, for example, then you do log of your argument divided by log of the base that you want. And this is how you change the base. So now let's take a look at this equation where we have two exponentials equated. So I'm going to start in a similar way. I'm going to take the log of both sides. I'm going to use my laws of logarithms to take that exponent as a multiplying factor out in front. And now what I'm going to do on the left side is I'm going to use the distributive property. I'm going to multiply this number log of 3 times x, and I'm going to do the log of 3 times 1, and I'll add those two things together. So here's what it looks like. Log of 3 times x plus log of 3 times 1, which is just log of 3. And I do the same thing on the other side. So you notice that we had 2x minus 5 times log 7. So I have log of 7 times 2x. So 2 times log of 7, that's the number part, that's the coefficient that's multiplying x. And then the other term is negative 5 times log 7. So from here I have something times x plus something, and here I have something times x minus something. This is an equation that you can solve by moving all the variable terms of the equation to one side and all the constant terms to the other side. And then you divide both sides by the coefficient of the variable. So here's what I'm going to do first. I am going to add 5 log 7 to both sides. The reason I do that is because it moves this constant term, this is just a number, over to the other side here. So here's what I get. So it's log 3x plus log 3 plus 5 log 7. So that is, we now have all the constant terms on this side of the equation. And now I want to move all the variable terms over to the other side of the equation. So let's go ahead and do that now. So I'm going to take away log 3x from both sides. And here's what I get. So now I have these two numbers combined into 1 on one side. And I have 2 log 7x minus log 3 times x on the other side. So this coefficient times x minus this coefficient times x. Now if I want to collect like terms, put those two things together, I would take this coefficient and subtract that coefficient. So I've put all that together as the coefficient in front of this x. And now last step here to solve this equation, I divide both sides of the equation by 2 log 7 minus log 3. And this is the solution to the equation. Now, evaluating this is a little bit tricky. I'll tell you the value, 3.88. I think that a number of people, if you try to just evaluate this as is, you may have a little bit of trouble getting it right the first time. So the one thing that I would recommend when you're doing this on your calculator is you make sure that you put the entire numerator in brackets and then punch in your divided by sign, and then put the denominator in brackets, because that's how it's supposed to be evaluated, by evaluating the top, evaluating the bottom, and the last thing is top divided by bottom. So I'll show you what that looks like on a calculator right now. And I may have to flip back and forth a little bit, but we'll see how it goes. So I'm going to go to the next line and I'm going to open up the brackets and I'm going to do log of 3. And now, see, I've forgotten already. Plus 5 log 7. So plus 5 log 7. Close the brackets. And then I divide by, put the entire denominator in brackets, although at this point, because Desmos has set it up in this way with a numerator and denominator, I probably could get away with leaving the brackets off, but just for those of you using different calculators, you'll definitely want to use that parentheses around your denominator to make sure that all of the denominator is being evaluated first, and then last thing, top divided by bottom. Okay, so let's take a look again at what that denominator is. So it's 2 log 7 minus log 3. So it's 2 log 7, 2 log 7 minus log 3. Okay, let me make sure that I do have that denominator right. So 2 log 7 minus log 3, yes, that is the one that I want. Okay, so I'm going to go back here, and it's evaluated. It is approximately 3.88 when I evaluate that to 2 decimal places. Now, for those of you who find this a little bit confusing, like maybe you were able to follow up to about... let me just change pen color here. So let's say, for instance, that you were okay up to this point, but then after that, it's a little bit like, what? Okay, so let me just clarify a little bit. When you have something like x plus 1 and you're multiplying by a number. Now, the number in this case is log 3. But let's say, just to do a simpler example, the number is just the number 3. Okay? And on the other side, we've got 2x minus 5. And then we've got a times log 7, which again could be confusing for some people. So let's say it's just a number. Okay? So the process is we expand the brackets. So I do 3 times x and I do 3 times 1. 3 times x plus 3 times 1. And I do 7 times 2x, that's 14x. And I do 7 times negative 5, that's negative 35. Well, essentially, that's the same thing that I just did here. I did log 3 times x, right, instead of just 3 times x. And I did log 3 times 1, which gives me log 3. Just like I did 3 times 1 here, that's 3. And on the other side, I did the same kind of thing. Just like the 7 times 2x, I would do log 7 times 2x. So I multiplied the log 7 and the 2. That gives me the coefficient of x. Just like 7 times 2 gave me the 14, which is the coefficient of x here. And then I do log 7 times negative 5, which is 5 times log 7. Obviously, those are the same thing. Just like I did 5 times 7 here gave me 35. So, if you're okay with that, but then you might be wondering, okay, well, hang on a second though, because what about the next step? Maybe you're a little bit confused on that. So I'll do a comparison with a simpler looking equation so you can understand why I did what I did. So what I did in that step was effectively moving this constant term to the left side of the equation. Just like here, we want to get to the point where we have x equals just a number, right? We're trying to figure out what that number is. So before we do that, we need to make sure that we have, all the variable terms on the left and all the constant terms on the right, okay? Or vice versa. So here's what I would do. Okay, so similarly to what I've done here, I've decided to move the constant terms to the left. So it's like adding 35 to both sides. If I add 35 to both sides, I get 38 here on the left, and I still have my 3x. And then I have 14x. So just compare that with what we have here, which is we've taken a constant term and we've moved it over to the other side. There's the 5 log 7 effectively moved to the left side of the equation. So this log 3 plus 5 log 7, that's the constant terms put together on the left. Just like the 35 and the 3 were put together on the left here. So it's the same thing. If you already understand what I'm talking about, that's fine. I know that people sometimes look at this work and get a little bit confused. So I'm trying to show you a simpler example and then draw the comparison so that you understand why I did what I did. And again, if you didn't understand the next step here, like what was going on? Why are you subtracting log 3x from both sides? Well, it's because, again, what we want to do is we want to end up with x equals an answer, which means we need to have x on one side and just a number on the other side. So in order to do that, I either need to move all the x's to the left side of the equation or all the x's to the right side of the equation. I'm deciding to move the x's to the right side of the equation. So that means I'm going to subtract 3x here, and I subtract 3x here. And what I get is 38 on the left and 11x on the right. Now let's just compare that with what I've done here. So I've subtracted the variable term from the left, and I've subtracted the same thing from the right because an equation is a balance and I have to maintain the balance. And so when I do that, just like I subtracted 3x from the side, I subtracted 3x from the side, I get 11x, which is 14 minus 3 times x. Here I have 2 log 7 minus log 3. That is the coefficient of x here. So now you might be wondering, well, what about the last step? What's the deal there? So let me draw a comparison with this simpler equation. In order to solve this equation that says 38 equals 11x, I would divide both sides by 11. And that gives me x equals, and you can put it in a bunch of different forms, 38 over 11, or you could change it to 3. 3 times 11 is 33. There's another 5 left over, 3 and 5/11. Or you could write it as a decimal, 3 point whatever, whatever. I'm not sure what that is, but that's okay. So there's a number of different forms that could be in. So in this case, what I did, again, was divide both sides by the coefficient of x. The coefficient of x here is quite a long expression. It's 2 log 7 minus log 3. So I divide this side by 2 log 7 minus log 3. And I divide the other side by 2 log 7 minus log 3. And now this entire expression is what I need to evaluate to get my answer. And that's it. So hopefully drawing the comparison with a similar equation that's a little bit simplified helps you to understand that a little bit more. And if not, feel free to reach out to me and ask me the question directly, and I will certainly follow up with you. All right, so now that we have a little bit of knowledge of how to change bases, you should be able to evaluate things like this. Now, you can do it like this, okay? Use the change of base rule. Okay, so the change of base rule works like this. If you want to do log base 4 of 10, you can take log base 10 of 10 divided by log base 10 of 4. So you take log base 10 of what's called the argument of the logarithm, and then divide by log base 10 of the base that you're looking to change to. Now in this case, log base 10 of 10 is just 1. So here's the simplified expression that you could have here. If you wanted to get it as decimal, you could evaluate it would be 1.66. Now for those of you who already have different base worked into your calculator and you know how to use that directly, then absolutely go ahead with that. And now the other thing that you may want to think about is, does this seem reasonable? Like, I know 4 to the 1 is 4, 4 squared is 16, so 4 to the 1.66, does that make sense that it's about 10? And I would say yes, that does make sense. So, and likewise, you may be thinking the same thing. Okay, 17 to the 1 would be 17. 17 squared would be 289. Oh no, that's going in the wrong direction. 17 to the 0 is 1. Okay, so it's got to be somewhere between 0 and 1 as an exponent on 17, which would give me a value of 12. So I know roughly where it's going to be now, and I can use either a change of base or doing it directly in the calculator to work it out. So log of 12 divided by log of 17 works out to 0.88. And this is the answer I was expecting. So, because it's between 0 and 1. All right, let's move on to an application question here. We're looking at a radioactive substance. It's called lead-210. And for those of you who don't know the physics behind this, basically what we're talking about, lead is an element that in this form, its atomic mass is 210 atomic mass units, and it will decay over time, and after 20.4 years, you will have half the mass of lead-210 that you started with. So this is what we call the half-life. It's the amount of time that it takes for this element in this form to decay to half its amount. And so if we are starting with 250 grams of lead-210, we want to know how much will be left after 35 years, and we want to answer to 2 decimal places. So let's use an exponential function to model this situation. And here's what it would look like. So I'm using capital A to signify the amount of lead-210 left after T years is going to be the initial value, 250 grams. And we're multiplying by 1/2 because, of course, we're using half-life. So it's going to a half in 20.4 years. So you can imagine when T is equal to 20.4, 20.4 divided by 20.4 equals 1. So we'll be multiplying by 1/2 once. And when T gets to 40.8, 40.8 divided by 20.4 is 2. We will be halving it twice. So times a half and times a half again. So this is how the radioactive decay will play out based on this mathematical model. And so now if we want to know how much will we have after 35 years, we can just substitute in T equals 35 into this function. And when we evaluate this, you will find that it is approximately 76.11 grams. Now, again, I'm talking a little bit about, think about your answer afterwards. Does it seem reasonable? So think about this. Okay, 35 years. So we get half the amount in 20.4 years. We get a quarter of the amount in 40.8 years. So this is kind of like between 1 and 2 half-lives. That's how long 35 years is. Well, if it was 1 half-life later, we'd have 125 grams. If it was 2 half-lives later, we'd have 62.5 grams. And this is in between those two values, so 76.11 grams, that seems reasonable to me. The next question is, how long will it take to have only 100 grams left? And so what we're going to do is we're going to take this exponential function and we're going to equate it to that value of 100. And now we're going to use our tools that we've developed for solving exponential equations using logarithms and go from there. So first I'm going to divide both sides by 250. It isolates the exponential part, the 1/2 to the T over 20.4. Now I can take log of both sides, or if I take log base 1/2 of both sides, then I go a little bit more quickly to my answer. And so if I do log base 1/2 of 1/2 to the T over 20.4, log base 1/2 and 1/2 to the power of, those are inverses of each other. So I just expose this, the exponent, T over 20.4, I get that isolated. And log base 1/2 of 2/5, well, this is what it is. Okay, so I'm going to be evaluating that and then multiplying by 20.4, and this will give me my final answer, which you can round off to a whole number of years because it indicated in the question you can answer to the nearest year. So now there's a final question, which is kind of an interesting one. It's asking you how long before it was 250 grams was there 300 grams. So if you trace back in time to before it started with 250 grams, there must have been more previously. So we can work back in time and work that out. So let's start with the exponential function on the left and the value we want to get to on the right. We're going to start by isolating just the 1/2 to the exponent part. Take log base 1/2 of both sides, as we did both previously. And then multiply both sides by 20.4. And now check out the value that we get here. It's about -5. Now -5 years, what's the deal with that? What's the deal with the negative? Well, the reason that it's negative is because this is in the past. So approximately 5 years ago, there would have been 300 grams of this lead-210. Cool beans. All right, final question. So we want to solve this for x. And this is a logarithmic equation. So we've got log base 5 of x minus 6 equal to 1 minus log base 5 of x minus 2. So here's what I'm going to do. I'm going to do 5 to the power of both sides. So I looked at the base, which is 5. And in order to undo this logarithm, I'm going to do 5 to the power of. And I'm going to do the same thing on the right. And now I'm going to use my laws of exponents to simplify both sides. So the left side is pretty simple. 5 to the power of and log base 5 are inverses of each other, so we just get x minus 6 on the left. On the right, let me just do a little bit of explaining. So 5 to the 1 is obviously here. And then since it's a minus, when you're subtracting exponents, it's because you have 5 to the 1 divided by 5 to the log base 5 x minus 2. So 5 to the power of log base 5 of x minus 2, 5 to the power of and log base 5 are inverses of each other, so we just get x minus 2 that results here. And so now what I'm going to do is I'm going to put the x minus 6 over 1, so we see we have what's like a proportion here, and we can cross multiply to get equivalent things. So I do x minus 6 times x minus 2 and 1 times 5 to the 1. And now if I expand the brackets here and then move that 5 to the other side, I have a quadratic equation. Now I can solve that quadratic equation by factoring just by looking for the factors of 7 that add to negative 8. So that would be negative 7 and negative 1. And now you can see x is either 7 or 1. Well, now let's think about whether both answers are reasonable. So first of all, we have restrictions on logarithm. You can't take the log of anything negative. You can't take the log of 0 either. So this x minus 6 has to be greater than 0. The other argument, the x minus 2, also has to be greater than 0. So x has to be both greater than 6 and it has to be greater than 2 as well. Well, as long as x is greater than 6, it will also be greater than 2. And obviously x equals 1 is less than 2 and it's less than 6. So x equals 1 must be rejected. And if you think about trying to plug in x equals 1 in here, 1 minus 6 is negative 5. Can't do log base 5 of negative 5. And if you do 1 minus 2, it's negative 1. So you can't do log base 5 of negative 1. And so x equals 1 has to be rejected. And so the only valid solution is x equals 7. You can substitute x equals 7 into that equation and you'll find that you get a value which makes the left-hand side of the equation equal to the right-hand side of the equation. So when you're looking at logarithms, here are the restrictions that you can keep in mind. So first of all, we've talked about the fact that the argument must be greater than 0, but don't forget that the base also has to be greater than 0, and we don't use a base of 1 either. So that concludes this lesson on solving exponential and logarithmic equations. Hope you understood that well, and thank you for watching. Have a great day. Bye.